All right, well, unfreeze. The maximum value, or when we're talking about function values, or the value of a function, we're talking about y values, right? You can always think about that as the y value. What's the output when I give it input? That's often how we think about functions and this kind of thing. So the maximum value of a function, as long as it's continuous on an interval, so it has a derivative everywhere, the limit exists everywhere. We remember all those ideas about continuity that we discussed a couple units ago. So in a given domain, and you'll see when we start examining examples, we're looking at maximum and minimums in a given interval. In grade 10, when you start looking at parabolas, you talk about the maximum value of a parabola. And we can talk about that because we know the nature of a parabola, that if it's opening downwards, it comes up, it turns, and it goes down, and it keeps going down. And now we know so much more about polynomials. We really get it. But we know that, like, the end behavior, that quadratic is going to go down forever, so it has a universal maximum. But what if I have some other kind of function, like maybe it's a trig function, sine curve, or some kind of polynomial function, or some kind of rational function that does all kind of wonky stuff? It probably won't, or it may very well not have a universal, or we call them global maximums, because the end behavior will eventually go up, right? And maybe the end behavior will eventually go down forever. Or if it's got a vertical asymptote, maybe it kind of does both halfway through, right? So it may not have a global maximum, but it would have local maxes, local mins. So it's the same concept as the max or min value of a quadratic, but in a more interesting graph. Instead of looking at the entire function, we maybe just take a snapshot of one part and we start thinking about where are the max and min values in that part. And this has major implications for real life because a company might be looking for when their max profits will occur, or maximum costs or minimum costs. Like, there's all kinds of times where you want to optimize. If you're writing code, computer code, you look at optimizing your code, so the minimum runtime of a loop of code or something like that, right? So there's all kinds of real world implications of optimization, maximizing and minimizing. And we do that by modeling these things with a function and examining the behavior of that function. Okay, so that's what we're talking about. So a maximum value can occur at a peak or a cusp. We'll look at what a cusp looks like in a moment. So we'll look at what a peak looks like. And the minimum value can occur at a trough. We call that a trough. So if I take a curve here, and you can just draw some kind of curve that's similar to mine, okay, like that. And so the curve, sure, continues on beyond this interval. Those black lines are designating the interval that we care about. Maybe one of those intervals is starting at 0. We talked about this the other day. If it's time, you probably have a sort of real life start at t equals 0. We don't go back in time typically. And then who knows what the other interval is. Or it might be a made up interval, I don't know. But for some reason, we've got an interval. We're only looking at the function inside this interval. So this would be my A, and this would be my B if I'm looking at the A's and B's between those values. So obviously, in this interval, the maximum value of this function is here. And the minimum value is here somewhere. And we see that those are smooth curves. So that's when we're talking about a cusp, or a peak or a trough. We're talking about like a smooth transition, a smooth curve from increasing to decreasing or decreasing to increasing. We've talked about those kinds of terms in the past. Or like, the kind of thing that you would see in a parabola. The kind of curve transition you would see in the vertex of a parabola. That's what we're talking about. What do we know from the limits and calculus and derivatives that we've done so far in MHF and in this course? Y prime will equal 0 at both of those positions, right? The slope of the tangent will be 0 at both of those. So right there we start to see that if I can determine where the slope of the tangent, where the derivative is equal to 0, I can find peaks and troughs. Okay? We're going to come back to the notation. The second place where a maximum or minimum value could occur on a given interval is an endpoint. So I might have a graph that goes like this. And again, it would continue on. Who knows what it does? I don't know. But I have a max here and a min here. And there's nothing particularly special about those points. Not like the derivative is something, has some characteristic there, because that's just randomly where the interval ended. And we could change where that, like that's, you know, could be chosen at random. There's nothing special about that. And then the last little grid that we have here is to just demonstrate what a trough looks like. So I might draw something like this. And so here I've got a max there and a min here. And at those points, what do we know? Does anybody remember what we know about the derivative at those locations? We briefly talked about, I think. That's right, it does not exist. Very good. Right? Because it doesn't have that smooth transition. This was actually something we talked about in the first unit. And so there we go. So now we're seeing it. Those kinds of graphs don't come up. There's got to be a pretty specific kind of function that's going to have that kind of a cusp in it. But they do exist. I think there's one, we see one example. We're not going to graph it, but we'll see a function that would have that kind of a cusp in it. And so we'll see what it looks like for the derivative to not exist. Okay. And so all of those points we call critical values. Not so much the ends of the interval. We don't really call those critical values, but we need to consider them as well. So peaks, troughs, cusps, those are all critical values. We can figure out that there are critical values by examining the first derivative of a function and testing those functions. And if I test the intervals and all the critical values, I'm going to find the max and mins on that interval. That's where we're going. So the first thing is we have to find those critical values. And the next thing is test them, because they may or may not be intervals. Intervals. In the interval, they may or may not be the max. I could have done an example here where you have like a cusp, but it's not the maximum value, right? You could visualize what that would look like. So keep that in mind. We do have to test and see. It's not a given that something is a max or a min just because it's a critical point, critical value. Okay, so some notation. This is just a reminder. We're talking about intervals. So I think we sometimes use, this is what we would usually call set notation. And what's interval notation is what we're going to look at. And I did interval notation in MHF. We used it a little bit. We talked about it, introduced it. We didn't use it that much, a tiny bit. We did talk about it, but I don't know, some of the other classes may not have, so this may be your first time seeing it. And because we're talking about intervals, it may come up. I think the questions that we're looking at today are actually still given in set notation. But anyway, this is an important notation, something you certainly should know. So if we're going to write the matching like situation for each of these, but in interval notation. So what's interesting about this one is it's going from A to B, and it includes A and includes B, right? So X is in the interval between A and B, including A and B, because it's less than or equal to A, or A is less than or equal to X, which is less than or equal to B. So how would that look in interval notation? Square bracket, minimum value, comma, maximum value, square bracket, because it includes both. Always minimum first, maximum second. Minimum value of the interval, not minimum value of the function. That's kind of unclear. Don't get confused about that. Okay, and then if I'm including A, square bracket, but not B, in interval notation, how do we show not including the endpoint with a round bracket? So really, you just got to remember square bracket means including the point, round bracket means not including the point. That's about it. There's not really anything else interesting happening. Oh, these ones are all wrong. So this one should be like this, I think. Yep. And then that would just look like that. Why don't you try the next one would be like that. It should be pretty easy. Oops, I messed that up. So if it didn't include either of those, obviously it's going to be just A comma B. Kind of looks like a Cartesian coordinate. But the last thing that's maybe not as obvious is how would you show just not an interval that's bound on two sides, that's only got a lower bound or only got an upper bound? Well, we use infinity. So if it's greater than A, it's going to, and it includes A in this case, it starts at A and goes to positive infinity. Never include positive infinity because it's not a number that you can actually get to, so that would always be a round bracket. And if it's less than B, that means it can go all the way down to negative infinity. So we start at negative infinity and it goes up to B. So again, the order of those technically does matter. If you wrote it out of order, people would be confused about what you were trying to say. They might guess, but it wouldn't, I think, be clear. Everybody okay with that? Now, I believe at the bottom of your page, it's on the next page of mine. Let's just take a look at the extreme values algorithm. I think if you get this idea, it's kind of obvious, kind of straightforward. But some people like to have steps, clear steps that they can kind of count through step 1, step 2, step 3 to make sure that they've done everything. So if we're trying to find the maximum y values or maximum function value or maximum value of a function of a given function in a given interval, okay? So we're going to find all x values where as I said before, where the derivative is 0 or doesn't exist. Those are called critical values. We talk about them enough that I guess it's useful to have a name for them. And that's really, like, step 1 is just, we're going to do that. We're getting everything prepped. So we're going to have a bunch of x values when we're done that. That's what we will have solved for. And steps 2 and 3 kind of go together. We're going to find the y values, the function values, at each of those x values, both end points of the interval, because as we saw, those could be the max or min values. And every one of the other critical values, we're going to find the y value at all those points. And then just compare, and then we'll know which ones are the max and the min. So steps 2 and 3 are giving us a bunch of y values. We look at all those y values and we just decide, to finish off the question, where is the local max, local min? Any questions? Pretty straightforward. Okay, let's take a look at this example. You don't have to write down the whole thing. Find the max and min values of each function on a given interval using extreme values algorithm, blah, 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 right? But illustrate your results with a sketch of the function in the given interval. So what do we have here? We have a cubic. We know a lot about cubic. We know a lot about polynomials. We know quite a bit about cubic functions. We know the kinds of shapes that it could take. And so I can already start to sort of match it up to the little sketches that we did on the first page. But I don't know what it looks like in that interval. I mean, for that matter, it could just look like this, right? It could look like a straight line. Parts of cubics will look like straight lines if you zoom in on that one part. If you don't get the interesting part, it could go like this. It could go like this. We just don't know. And so we're gonna see what happens overall, but then zoom in on that interval and figure out what's happening. So the first step is take the derivative, and I'm going to mark steps 1, 2, and 3 just for the first example, but that's not something you need to do. So the first step is to find the x values where the derivative is 0 or does not exist. So we first have to find the derivative, obviously, so we've got that. And again, like I might not write this out every time, but now we're going to find where f prime at x equals 0 by setting it equal to 0. And I hope it's obvious we're going to solve this by factoring. And our understanding of functions in general is so important because I have to be able to examine that and also tell that f prime at x exists for all x, right? It exists everywhere because it's quadratic, it's polynomial. So I don't have to worry about that part. There's nowhere where the derivative does not exist. So for this example, that part, we don't do it. Oh, I didn't quite finish this. So this is where x equals 4 and negative 2. We good so far? Very simple, straightforward. So something I notice is one of these two values isn't in our interval. So when I was drawing those pictures before and I showed how like maybe the cubic is turning outside the interval, entering the interval, turning again, and then exiting, like that's apparently what this one's looking like, I guess. Because this one is not in our interval. From negative 5 to 3, not in there. So we don't have to worry about it. And sometimes we get caught up in what we're doing so much that we forget about those little details, and you go ahead and you find that value and call it a max or call it a min or just do extra work that you don't need to do, right? But so you've got to maybe force yourself to double check every critical value, every place where the derivative is equal to 0 or does not exist, and ask yourself, is it in the interval? And often they will be. So again, we forget to double check that, but we do. Okay, so that was all of that was step 1. Step 2 is find the function value of each of the x values in step 1. So there's just one. So f at negative 2. Plug that in. Now we're going back to the original value. Don't make that mistake and plug it into the derivative. I don't care about the maximum values of the derivative. We're looking for the values of the... In fact, if I put that into the derivative, I'd get 0, right? That's where that came from. But we're going back to the original function. And that is definitely something people get confused when we, later on this week and after the March break, we start to add in second derivatives to this process. You forget about like which one you're you're dealing with or which one you're caring about at the time. Okay. And I believe it works out to 38. You can double check that for me. And then step 3 is find the function value at each of the endpoints. So f at -5, right? And f at 3. And I got -70 and -62. Everybody okay? We're supposed to draw a sketch. So here's my interval. This is -5. This is 3. At -5, my value is 70. That's the minimum value. At 3, my value is 62, so it's a bit higher, but it's still low. And at -2, which is over here somewhere, I'm at 38. And so, 38, -70, -62, 2. So I'm going to go up, make sure that's an actual peak, and then, kind of nasty, and then it's going to go down again and go up like that. I'm going to stop it here and kind of do a dotted line, right? Because I know that there's another critical point there. It's going to be a turning point, right, where the derivative was equal to 0, but we don't care about it because it's outside. But it's always nice to think, we know a lot about these functions, so I can figure out what the rest of it looks like. That's a good thing. We're going to be doing curve sketching later in this unit where we have to think about what these curves are doing and where they're going, so it's useful to start thinking about that now. Any questions about this so far? And therefore, we got to state the maximum. Therefore, the maximum is 38, and the minimum is -70. Yep. Where they, no. I believe find the maximum and minimum value. I absolutely could imagine a question that says, and where they are located. Well, if the question said that, then yeah. But other questions? All right, let's try another one. All right, I think you're ready to start this on your own. Give it a try. What's the first step? Just think through that. Look at the first example. It's pretty straightforward. Go ahead and give it a shot. You check your first line of derivative against mine. Make sure that's right. But we're going to expand and simplify. We got to solve this for 0, right? Like that's what we did in the last unit. You now see why the second day of that full simplification we were determining where the derivative was equal to 0 does not exist, because now we're using those ideas to examine things about the functions. So all right. How many people have that as their last line? We get that? Now we get to start examining it. Sia, can you share with the class what you just told me? Yeah. So just I think what you're saying is it's rational. It's got stuff on the bottom, so that could be a place where it doesn't exist. Good.
But then I did the whole lesson with 0,
Mm-hmm.
and it doesn't work out because since it's x squared, then any x value that you put in will be positive.
Very nice. So if I put, like, if I want it to not exist, I have to get 0 in the denominator. How do I get 0? If I'm going to add to 1, I've got to make this -1. But that can't be -1 because no matter what you throw at x, it's going to square it and make it positive. That's a great way of just thinking about the algebra behind why that will not happen. And f at x exists everywhere. There's nowhere that it does not exist. Algebraically, we could do it like this. X squared plus 1 all squared equals 0. Where will that occur? So take the square root of both sides. Move the 1 over. And then we see maybe a little bit more straightforward, the square root of -1. If we're talking real numbers, that's not going to happen. You go to imaginary numbers, complex number system, and math changes drastically. But for real numbers, which is what we're talking about, we don't have to worry about it. Okay, very nice. So that's not possible. So we are good with that. So now we want to go on to where f prime at x equals 0. And so that's where the whole function 8x, x squared plus 1 squared equals 0. But I know that it's really just the top that I care about, right? Don't get too caught up in the shortcut that we take where we only really care about the top. It's the whole function equals 0, but I know that can only occur when the top equals 0. And in that case, it's pretty trivial. That's in our interval? Yep. So I'm going to go and I'm going to check that point. This would be step 2. And I'm going to check the bounds of our interval, which are -2 and 4. Now figure those out. Are those values correct? Anybody check them? Oh, frozen. So therefore, the minimum value is 0, and the max is 64 over 17. And if we want to sketch this one, so the minimum value occurred at 0, and the derivative was equal to 0 there. So that is a turning point, right? We may not know exactly what the function looks like, but that part doesn't, without doing more of the work, especially around a rational function, but that part doesn't matter. We know it's a turning point. Let's see. The -2 value was about here, let's say. And then the 4 value was a bit higher, so it came down and turned somewhere and went back up. Any questions? Okay, let's try one more. Okay, so again, go ahead and take the derivative. First line's pretty easy, I think. You should get that. But then we need to simplify this. So there's a couple of ways you could do it. Go give it a try. So you might approach this question in a couple of ways. I can common factor out some of the parts I don't like, or some of the parts that are, in this case, going to make it work nicely. So I'm just going to pull the fraction out because there's a 3 in both. Why not? And then I see that 5 is common in both 5 and 20, so I can factor out the 5 over 3. And then what's going on here with these exponents? Well, I noticed that if I probably want to fully factor one of them. Maybe that's not going to work, but if I can, and if I divide, this may be a bit tricky if you've never quite done this before, but if I divide x to the 2/3 divided by x to the negative 1/3, I subtract the exponents. That's actually 2/3 plus 1/3, which is 1. So maybe it surprises you, but you end up with x. And I just end up with x minus 4. Because 20 divided by 5 is 4, so I've just got that. So that's a quick way of sometimes those, you can factor those. The other way would be by writing it out as a fraction and coming up with a common denominator. So what would that look like? I would multiply the first bracket by x to the 1/3 over x to the 1/3 to get a common denominator, right? And again, x to the 2/3 times x to the 1/3, I would add those exponents, the same thing. So I get 5x minus 20 all over 3x to the 1/3. And then I would factor the top. So 5 times x minus 4 over 3 times the cubed root of x. And I want to do the same thing here, write it as a fraction. Oops. F prime at x equals 0 where? It's already factored, so I don't need to show the work here. I can just state it from this factored form. Yeah. 4. And f prime does not exist where? Good. Because that would make the square root of 0 is 0 times 3 is 0. That would make the denominator 0. So if we fully simplified the derivative properly, fully factored it, then we can kind of just state the critical values in this step. The other ones we didn't, we factored afterwards for whatever reason. Both of those are inner interval. Our interval was -2 to +6. So yeah, we're good. So I've got a bunch of values to check. So why don't you go ahead and try that? I'm going to let you check them all just because sometimes, again, we do all this crazy math and then we make a mistake punching it into our calculator. So I'll give you a chance to do some of that grunt work. All right, let's see. Did you get this? I think I got, some of these I'm just going to round, right? So this is about 19.0. F at 0 is 0. This is something that we need to talk about. F at 4 was about 15.1, negative 15.1. And F at 6 was about negative 13.2. Does anybody confirm those, or any of them look wrong? Do they look okay? Let me know if those are wrong. So I want to show you something. This is an important detail because we found right here that the derivative does not exist at x equals 0, but then we evaluated it and got 0. So this is an example where the function exists, but the derivative doesn't. And again, we've talked about those, but let's take a look. So on the left, this green function is our original function, and on the right is the derivative. And so look what's happening with this, with the original function, the green one. It's got a cusp. Okay, so it happens to be one of the ones, we don't see them too often, but it's a cusp. And then what does it do the rest of the time? It goes up that way, going that direction, and going the other direction kind of looks like it's curving down that way. Not that it really matters, but just interesting, different kinds of functions we can see. And then, but take a look, because the derivative ended up with that denominator, the derivative has an asymptote. So the derivative doesn't exist, and we see graphically what that means. Cusps do not have derivatives, right? But the function exists at that point. The fact that it happens to be 0 is not important. It could be another value, right? So we got that. So therefore, the max is 0 because the others are negative. This was supposed to be negative 19.0. Did you guys check my answers at all? Jeez. And the min is negative 19.0. And we kind of saw what this looks like. But at negative 2, it's at the minimum. It goes up there. And then it goes down. But not as low as the minimum, obviously. And then back up. And I know that that's a cusp because the derivative does not exist. It's different from equaling 0. Yeah. Yeah, approximately would be a nice idea. Yeah. Approximately. Yeah. Okay. Any other questions? So this is negative 19.0. This is 0. This is negative 15.1, and this is negative 13.2. All right, there you go. Page 200, question number 2, 3C, E, and 4.